you got 15 minutes, please.
Thank you. My name is Luana. I'm a PhD student from Unicamp, and I am part of the Laboratory of Applied Computational Electromagnetism from Professor Figueroa. This work has been done in partnership with CCS Nano, Center for Semiconductor Components and Nanotechnology, the clean room from Unicamp too. And I'm here to talk about synthesis of pure phase titanium dioxide films without direct external control applied to the fabrication of optical structures. So this is the outline of my talk. First of all, during the introductions, I will show you our motivations and objectives with this research. This work has two parts, two moments. The first one is the fabrication of titanium dioxide films, where we talk about the deposition methodology and the characterizations of these films by Raman spectroscopy. And the second moment is the fabrication of titanium dioxide waveguides, where we talk about the waveguide fabrication methodology and the image characterization of those waveguides by optical microscopy. And then I will show you the contributions of this work and the future work that our group has in mind. So the first question that we have to answer is, why has titanium dioxide been studied in optical application? In fact, this material has been famous along the years, and there are a lot of reasons for this. But here I want to highlight three of them. This material has high refractive index, chemical stability, and this material has very interesting optical properties. Specifically in this work, we are interested to work specifically with anatase phase. And why we use anatase phase? This material can be found in three crystalline phases: the anatase, the rutil, and the Brookite phase. We have three reasons for our interest. The first one, specifically this phase has a higher refractive index, so for optical applications it's important. This crystalline phase has application in ultra-efficient catalytic optical devices, and this is a hot topic on the literature. And this crystalline phase has lower losses due to scattering. However, to take advantage of these properties, we have to work on pure anatase conditions. But to achieve these pure anatase conditions with good quality and reproducibility is particularly challenging because the lack of temperature control in some commercial sputtering equipment, and this lack of temperature control can cause wanted phase mixing, mainly between the anatase and the rutil phase, and we don't want to work in these conditions. So, trying to overcome this problem, the mixed phase problem, here we have our proposal is to develop a process where the deposition is discretized on time. And we call this process by multi-step process. So according to the outline of this presentation, here we have the first moment, the fabrication and characterization of titanium dioxide films. First of all, I will show you the methodology for this deposition. First, the single-step process, the traditional process of sputtering, and the multi-step process, our proposal here. And then, as a characterization, we will discuss the Raman spectroscopy to compare the puritativity in each of these processes here. So here we have a photo from our equipment used on this research. The first diagram here shows the single-step process, and the second diagram shows the multi-step process. The single-step process is a traditional process of sputtering, where we have the parameters of deposition, argon flow, oxygen flow, chamber pressure, DC power, and the current. Here, as we want to achieve 150 nanometer thick, following this our recipe, we have 30 minutes of deposition. During this time, all these parameters here is still working. But we notice that this exposure time is long enough and it causes the wanted temperature increase, and consequently it starts this phase mixing between the anatase and the rutil phase, and we don't want this condition here. So trying to overcome the situation here, have the same parameters of the position, but here we have discretized the time deposition on time. Every 10 minutes we achieve 50 nanometer tick. So the first step is just 10 minutes of deposition. Here we have little times, little blocks of deposition followed by little blocks of a break. So after this 10 minutes here, we have the time of a break, 5 minutes between each cycle, and during this time here, only the argon, oxygen flow, and the chamber pressure is still working. Here we have to shut off the DC power and the current. After this process here, we come back to this time of deposition, make more 10 minutes to achieve more 50 nanometers tick, and we continue the cycle to obtain 100 nanometer tick. Of course, we can stop before, or we can continue this cycle. It will depend the thickness that we want. But the fact is, with this method, we are able to avoid the temperature increase even if we are working with an equipment that doesn't have direct temperature control. That's the point of this work. So, to show you what I'm saying, here we have the Raman spectroscope. The blue line is the single-step process, films produced by single-step process, and the yellow line are the films produced by multi-step process. As we can see here, the peaks from anatase and the root to the phase are well known on the literature. So when we make the deposition with the single-step process, we can see a peak from anatase, okay, but these two other peaks here came from the root to the phase. So when we apply the method, the little blocks of deposition followed by little blocks of a break, we are able to produce a film in pure anatase condition. This first peaks here comes from the anatase, and these other two here the same. These results are well known in the literature, and with this method we are able to avoid this lack of temperature control with reproducibility. So this is the second moment of this work, the fabrication and characterization of titanium dioxide waveguides. Here, this step is to show you the compatibility between the multi-step process with lithography technique. In this case, we are studying the thermochemical lithography, the TSPL, and as a characterization, we are discussing the optical microscopy of this waveguides. Here we have a photo of from the equipment that we have at our lab, the TSPL. And here we have the diagram to show how this techniques works. Start by this one here. We have the PMMA and the PPA on silicon substrate, coated resists. This technique, this lithography technique, is a maskless technique, operates at room temperature and vacuum free. So these are good points of this technique. And here we have a probe. And this technique is based on approach, this hot and nanometric probe to this outer resist here, the PPA. And this technique, this outer resist here is thermally sensitive and submits optical contact with this probe. And when this probe makes this movement along the sample pixel by pixel, according to a previously designed, we are able to make the pattern on the PPA. But we have to finish to expose the substrate, so we continue to that etch process, and finally we are able to make the titanium dioxide deposition by multi-step process, as I described in the beginning of this presentation, represented by this red line here. So after the lift-off, in the end, we have a waveguide by titanium dioxide in pure anatase condition on silicon substrate. Here we have a same image of our probe. This dimension here has around 10 nanometer, and following these conditions of deposition of fabricate, the temperature of this probe is 750 degrees. So it's a very hot and nanometric probe. So here we have the optical microscopy of this waveguide fabricate post liftoff. We fabricated two waveguides, one half of the other. And here I want to highlight two points. The first one, we can achieve an ultra high resolution mainly at the edge, as we can see here by this image. because this technique doesn't have the intrinsic proximity effects found in electromagnetars. For in some of types of fabrication, it could be a good idea to use this technique. And the second point is that this dimension here of these waveguides have an error of less than 1% compared with the initial design. So in fact, this is a powerful technique, and our group has been developing a good background on this technique. And just to inspire you, here we have some of our expertise with this technique. This structure already fabricated by gold on silicon substrate, and here, following this scale here, we are able to see that we can achieve an ultra high resolution even if we have a high contrast between the dimensions, as you can see here. This dimension here has 30 nanometer and this one has 100 nanometer. So, to conclude my work here, I post the main contributions that we have. We successfully fabricated zinc oxide films in the pure anatase phase even without direct temperature control. And we demonstrated the compatibility of this methodology with the TSPL technique. And as a future work, first point, we are studying the propagation of the waveguide, and we are studying the fabrications of all the electric metasurface. And this is a hot topic too on the literature. And just for you see, here we have nanodiesels, a metasurface composed by nanodiesels. Here we have titanium dioxide in pure anatase phase, and here we have silicon dioxide substrate. And in this case, is a kind of challenge because we have to match the parameters, the position parameters of the TSPL technique and the sputtering. Because when we are working with all the electric material, they can be changed a little bit. So, thank you, they are my contact, and to know more about our facilities, we have this QR code here.
Thank you.